I am currently a beamline scientist at the NanoMax beamline at Max4 Lab in Sweden. But so this isn't a HAXPES beamline, it's a nanoprobe hard X-ray imaging beamline. But prior to that, I was a postdoc at the University of Cambridge, and we used some of the HAXPES resources around us to investigate hafnia-based ferroelectrics. So just a quick introduction to this. Hafnia has been used in the CMOS industry for decades. It's very industrially compatible, but it was discovered about 12, 13 years ago that it's actually also ferroelectric at ultra-thin thicknesses. And this has excited a lot of new research in ferroelectricity, both in hafnia and other materials. But the exact nature of the ferroelectricity of hafnia is still debated. So this is quite a complex material because the polar phase of hafnia is thermodynamically unstable. So it's sensitive to oxygen vacancy concentrations. And the oxygen itself is actually the dipole, like the atom that displaces to produce the dipole of ferroelectric hafnia. So then obviously it could be sensitive to oxygen vacancies. And finally, it's been observed that oxygen can actually migrate in hafnia at high temperature, but also at electric fields that are similar to those needed to polarize the material. So all of these point to a complex interplay between ferroelectricity and oxygen electrochemistry, and even going so far as to leading researchers to believe that perhaps there isn't any type of intrinsic ferroelectricity in hafnia, but in fact, it's just an effect of oxygen reorganization. So we want to better understand the role oxygen plays in ferroelectricity, and in particular, this migration or reorganization, how it affects ferroelectricity. So to do this, we designed two sample systems that we could use to better compare and try to decouple some of these effects. So the first one is our sort of reference sample, which is a hafnia zirconate stack, which is the most traditional hafnia ferroelectric. It's grown to an 8 nanometer thickness on lanthanum strontium manganate on top of strontium titanate. And this is grown using pulse laser deposition. And then to compare to this, we also made a more novel form of hafnia composition, which is hafnia that's doped with lanthanum and tantalum. So this is grown in almost the exact same fashion with PLD, where we grow 8 nanometers on the same thickness of LSMO and strontium titanate. And the goal here was to create something very similar to HZO, in that we'd have a balance of lanthanum and tantalum dopants that would charge compensate for the hafnia, because hafnia and zirconia themselves is a charge compensated film. But using PLD means we don't have 100% control. So in the end, we ended up with a bit of excess tantalum dopants, meaning we have a slightly positive charge doping. So there's a slight difference in the charge within these films. However, the structure of these films is really similar. They have equivalent phase, lattice parameter, and nearly equivalent internal strain. And then finally, looking at the ferroelectricity, we do see a difference between these two films, despite them being quite similar. We get a remnant polarization of around 4 microcoulombs per centimeter squared for HZO, and then slightly higher for HLTO. So now we have two systems to compare that are structurally very similar, but have different ferroelectric behavior. And we wanted to investigate these films looking at the oxygen behavior or the electrochemistry overall, not just at the top surface of the films, but at buried interfaces as well, like at the LSMO interface. So to do this, we decided to do HAXPES on a combination of XPS and HAXPES at the IO9 beamline at Diamond. And so using 1 keV X-rays, we could probe the top about 4 nanometers of our film. And then using 5.9 keV, we could probe deeper into the LSMO. We also used the lab-based HAXPES source at Manchester on the HZO film. And this 9.25 keV X-rays allowed us to probe all the way into the STO. And we also used the angle-resolved HAXPES in order to probe different depths in our sample. But if we want to connect the oxygen electrochemistry to our ferroelectric behavior, we of course need to observe some difference in ferroelectricity or do some kind of operando measurement. And what we chose in the end to do is more of an ex operando experiment. So this is a little bit simpler, where we use piezo response force microscopy, or PFM, to poll different regions of our sample, leaving them in three different states: P up, P down, or as grown. And we used alignment markers in order to find these regions again once we loaded them for HAXPES. And these regions of PFM were about 300 microns, which means that it was easy to make sure that the X-ray probe was fully within this region. So just to get into some of the results, first looking at the oxygen 1s spectra for HLTO. So this is at 1 keV and 5.9 keV. And the most obvious feature we can see here is that comparing between the P up, which is red, and then P down and as grown, we see this peak arise at 532 eV. Now, this peak is potentially controversial because it's often referred to as oxygen vacancies, but we refer to it as non-lattice oxygen because it's simply a oxygen species that isn't singularly bound to the hafnia or lanthanum or tantalum atoms. So it could be from a number of things, including surface hydroxyl or hydroxide formation, or bulk oxygen interstitials, or bulk hydrides. And while it's not direct evidence of changes in oxygen vacancy, it can be a secondary effect of vacancy reorganization. So it's quite complex, but we'll just call it non-lattice oxygen. If we look at the HZO, we can see the same peak arise, albeit at lower resolution, at 532 eV. And if we think about this briefly, many people would suspect that this peak comes from just the difference in atmospheric exposure of our sample. Maybe one sample was left out longer, or one sample was exposed to something slightly different before loading it into the UHV chamber. But in fact, these different regions of P up, P down, as grown were on the same sample, and they're just maybe 500 microns away from each other. And also, if we look at the carbon 1s spectra at 1 keV for HLTO, we can see that between all of these conditions, there's not much of a change in the carbon peak. So this suggests that this is not actually an effect of atmospheric exposure, but actually of the electric field that we have applied before our measurements. This peak has about a twofold increase for the P up condition, both for HLTO and for HZO. But in HLTO, we can see that this peak isn't as obvious at 5.9 keV, suggesting that mostly this non-lattice oxygen occurs at the top of the film. But then looking at the HZO, we can see that as you go deeper, looking at from shallow to deep in this angle result HAXPES measurement, we still see this peak present until we get so deep that we're really probing mostly strontium titanate. So in this case, we have non-lattice oxygen throughout our film. If we look briefly then at the hafnia core levels, we can see for 1 keV, we get a shift in HLTO in the hafnia peak. But this shift isn't a change in the peak shape, it's just a pure shift, which suggests that there's no change here in our stoichiometry, but instead some kind of field-induced shift in the P up condition. And then we see this mostly in the top of our film. We don't see it again once we're probing deeper at 5.9 keV. Then looking again at HZO, we also see some effect in the P up condition in the hafnia 3D spectra. And in this case, what's different is that this isn't just a shift, it's actually a broadening of our peak. This suggests that we're getting a change in stoichiometry, specifically a reduction in hafnia in the P up condition. And we see this throughout our film, regardless of depth, suggesting it's not just happening in the top surface. So to summarize briefly, we've observed many different things within our samples, and I've had to leave some of them out for time's sake, but in the HLTO, we see for the P up condition that non-lattice oxygen mostly increases in the top 4 nanometers of our film. Whereas for HZO, we can see anomalous oxygen throughout the entire film. And again, for the P-up condition, for HLTO, we don't observe any effect of hafnium or tantalum reduction or oxidation, but we do see a reduction of hafnia and zirconia in the P-up condition of HZO. I didn't show this data, but we do have some evidence that we have some LSMO oxidation when we have HZO reduction, but then no such effect in the HLTO. So what we think might be going on here is that when you apply a negative bias to switch your sample into the P-up condition, we can get negatively charged species that are being driven into the film and onto the film surface. But in the HZO, we actually are getting a local reorganization of oxygen with reduction of HZO and potential oxidation of LSMO. This isn't a mass migration, but just a really local reorganization that we seem to be observing. And the differences that we see here, why we get this reduction in oxidation of HZO and not in HLTO, could be for a number of reasons. One of them being that, according to DFT, it takes more energy to create an oxygen vacancy in HLTO compared to HZO. But also, we know that we have a excess positive charge from the excess tantalum dopants in the HLTO, which might benefit from drawing species from the atmosphere into our sample for charge balance effects. But ultimately, what's important here is that we're seeing a significant reorganization of oxygen in the material that actually has a lower remnant polarization. So what this suggests to us is that, yes, ferroelectric switching and oxygen migration co-occur. This makes sense given the need to balance electrostatics, and we observe this, and it's been observed before. But this doesn't necessarily mean that they're intrinsically linked, because we see less oxygen reorganization in the material with a higher remnant polarization, being HLTO. And so instead, we think this is just an effective electric field and less material and more material dependent, not dependent on the oxygen reorganization. So from this, we think that we're providing evidence of an intrinsic polar state in hafnia, better understanding the fundamental nature of this material. And we think that HAXPES could be used in a similar way with other types of device stacks, like ones who have actual metal electrodes on top, or to study similar polycrystalline material of hafnia, which is very interesting to the ferroelectrics field, or standard perovskites as well. But ultimately, this combination of XPS and HAXPES allowed us to probe different depths and better separate the effects of ferroelectricity and oxygen electrochemistry. And I think that many researchers could benefit from this same type of experimental design. So I just want to acknowledge my collaborators at University of Cambridge, particularly Judith Driscoll and Nevis Chakai, and Jisoo Kim, who was the student who grew these films, as well as the staff at University of Manchester and Diamond who helped support these experiments. And I do want to mention that now that I'm at Max 4, I'm not doing HAXPES at the moment, but we are in the process, not me personally, but Max 4 is in the process of applying for funding and doing a technical design to get funding for a new beamline, which would hopefully be implemented in the next 5 years, which is a HAXPES beamline ranging from 2 to 15 keV, and using the 4th generation high flux of Max 4 could be really powerful, with a spot size down to 3 microns and 3 different HAXPES instruments, both for permanent UHV measurements and for more in situ and flexible ambient pressure measurements. And then I've put the contact down here if you are interested in this development and what you could possibly do here in the future.